Hi there, this is Dave Nguyen, CEO of Continuum, and in this presentation, I'm going to show you how ShapeGenie has identified a continuum of composite morphologies of the cup and the disc that define normal versus glaucoma. First, let's talk about how ShapeGenie works. The core algorithm is the LCPC transform, which is the linearized compressed polar coordinates transform. And the way it works is in step one, here is the outline of your shape, and it is possible that your shape has two lines. ShapeGenie will then find the smallest bounding box that touches the edge of the object. The center of that bounding box will become an origin, the red dot. And in step two, that red dot is the origin of a radial grid system that overlays lines on your object. In step three, ShapeGenie then finds every intersection between the radial lines and your object. And in step four, ShapeGenie linearizes the data into two dimensions, x and y. The x-axis is the position of the angle, that is, of each radial line, and the y-axis is the distance from the origin. Now notice that in figure 3 we have two edges, but in step 4 we only have one line. And the reason is because all dots that are on the same line are summed together. So even though one radial line intersects the object twice, and each object has its own distance from the red dot, ShapeGenie sums all distances on the same line into one number. Thus, you have a discrete curve on step 4. Then in step 5, ShapeGenie will apply the fast Fourier transform on the data in step 4 to get a frequency spectrum. And this frequency spectrum is a multi-dimensional representation of the shape that you began with in step 1. Now you can analyze the shape data based on this multi-dimensional system of numbers, or you can derive a scalar value in the form of an index. For example, summing all of these blue bars together into one number would give an index that we call sum all bins. But first we have to talk about some critical details. The first one is that ShapeGenie can measure shapes both at scale, we call it, and in the form of pure shape. So at scale means that you're comparing both the size and the shape at the same time. For example, here the blue figure and the red figure are exactly the same figures, except I enlarged the red one. So in this case, they have the same shape, but different sizes. With ShapeGenie, we can do something very special. That is, we can resize both objects in a way that's objective, so that they, in this case, share the same height, so that now these two objects are both the same in size and the same in shape. So when we resize it according to its longest axis of difference, we always constrain the aspect ratio so we don't skew the shape. When we measure pure shape, what we're measuring is shape apart from the effect of size. Another advantage of measuring pure shape is that differences in magnification between images and data sets do not matter, because pure shape measures shape in a way that is scaleless. So it doesn't matter if you don't know the magnification of the various images that you are analyzing. Second critical detail is that we always orient shapes in a standardized fashion before we measure them. For example, step 1 is the outline of the cup and the disc in the image. In step 2, we identify the longest internal length of the cup, the inner ring. And then in step 3, we rotate the whole object such that that longest length is horizontal. And then when we want to measure pure shape, we resize the object so that its width is 400 pixels. Then we, out of convention, rotate the object 90 degrees clockwise so that its axis of greatest difference is vertical. We then send this shape for radial grid processing. Now note that all the outlines you will see in this presentation are of cups and discs that have been oriented in this way. So they may not look like the ones you would see in fundus images. For an overview of our analysis pipeline, we analyze each cup and disc shape and turn it into 71 values. So here in this table, each cell has 71 values. And again, this is a multi-dimensional representation of the shape that you began with. As an analogy, your age is a scalar value, that is, I am 40, but my birth date is a static multidimensional value, that is, I was born on April 12th, 1983. And though you can derive my age from my birth date provides a lot more information than my age does. Once we have obtained the data outputted by ShapeGenie, we do k-means clustering to identify subgroups, and then we do principal component analysis to find the greatest differences in that data set. We then plot the data according to the first two principal components while color coding the samples according to the k-means subgroups. Let's first talk about our normal patients. And here are the 4 data sets that we analyzed and the number of normal patients in each that we selected. So here's a plot of the first 2 principal components of the normal samples. The dots are color-coded according to the 3 groups identified by k-means clustering. And as a way of verifying that the k-means clusters are biologically meaningful clusters, we compare the morphology of the middle 5 samples in each region, and we found that these clusters represent distinct cup and disc phenotypes. On the right, the cup is a lot smaller than the disc, and on the left, the cup is larger. However, when we looked at the data points at the boundary regions, what we realized is that what ShapeGenie has measured is not distinct states of morphology, but a continuum of morphology, ranging from very small cups on one end to very large cups on the other. And it does so in a way that's multidimensional, because here we've only plotted the first 2 principal components. We can also plot the third one for a 3D plot, showing pockets in which not only does it matter that the cup is small, but it also matters what region, what quadrant of the disc it is located in. This level of nuance and precision is very exciting to us, because we believe that if we combine this data with clinical information about the age, sex, and pre-existing conditions of the patient, we will be able to identify subtypes of risk that correlate with different regions of the spectrum. The existence of subtypes is ubiquitous across all human diseases, and so when we see a continuum of what we call normal, we would expect to also find subtypes for the risk of glaucoma. Now let's look at our glaucoma samples. Here are the 4 data sets and the number of glaucoma patients that we selected. K-means clustering again found 3 groups, and these 3 groups represent distinct phenotypes that are ultimately points in a continuum of phenotypes. I want to point out that different regions of this orange category can have different combinations of shapes when it comes to the cup and the disc. Here, both the cup and the disc are elongated. While here, in this region, the cup is larger, off-center, and the disc is less elongated. Again, this level of nuance and precision makes us believe that if we had clinical data on the age, sex, and pre-existing conditions of the patients, we will be able to identify subtypes of glaucoma. What is the big deal about subtypes? Well, medical treatment often makes major advances when we discover new subtypes of a disease, because new subtypes allow us to create specific therapies that work just for that group, so that we spare the negative side effect from all the other groups that wouldn't benefit from that same drug or that same treatment. And to prove that the numbers produced by ShapeGenie can be used to make predictions on clinical outcome, we have built a preliminary machine learning classifier to classify normal versus glaucoma based on the shapes that we have measured. So based on the frequency spectrum we get from every shape that we analyze, we were able to find 3 shape indices quite easily, and here they are plotted as normal versus glaucoma. We have yet to do a deeper dive to find better indices, but the ones we have found so far have sufficed for the data that I'm about to show you. So we built a random forest classifier based on these 3 features, and though we trained with only 50% of the data, we were able to get an accuracy of 76%. As a way of improving the model, we realized that there are things that we can quickly and easily measure to enhance the classification of glaucoma. One is the traditional approach of the ratio of the cup to the disc. While traditionally people have measured the vertical height of the cup and the vertical height of the disc, we measured the longest internal length of the cup and the longest internal length of the disc and created a ratio of cup to disc. And this ratio separates normal versus glaucoma quite nicely. We also noticed in every data set that we've analyzed that the length of the cup is longer in glaucoma than in normal, but we could not use this feature because each data set imaged the cup and disc at a different magnification. Thus, I had to figure out a way to normalize it, and I realized that since the ratio A we calculated here exists in every single patient, we can simply multiply that to the length of that patient's cup to normalize the length of the cup as a universal feature that will work across all data sets. And we did so, and we found nice separation. So adding these two features to the previous three we found in ShapeGenie, though we still trained with only 50% of the data, the accuracy of our model went up to 82%. So the preliminary data is quite promising in terms of how effective ShapeGenie can be in producing data that leads to good machine learning predictions. In conclusion, ShapeGenie can measure morphological features of the optic cup and disc that no other technology can. And its outputs are highly interpretable because we know exactly what we're measuring, right? That is, it's the shape of the cup, the shape of the disc, and the position of the cup within that disc. Secondly, ShapeGenie is uniquely able to speed the discovery of unknown risk groups that are susceptible to glaucoma and unknown subtypes of glaucoma. Lastly, the results from ShapeGenie can enhance existing machine learning models that classify glaucoma based on deep learning methods. There are quite a few academic labs that have developed great models, and for-profit companies have commercialized their deep learning models to classify glaucoma. And all of these models can benefit from the way ShapeGenie measures morphology. Thank you for your attention.